Welcome back. In the next lecture of Fundamental of Electronics, we will discuss the bipolar junction transistor, the fundamentals, talking about the structure, doping level, the voltage and the current gain, and basically how the current flow in the BJT. First, let us start with the introduction to bipolar junction transistor. So the BJT was invented by William Shockley in the year 1951. The basic purpose of the BJTs are to amplify the electronic signal which are basically used in the radio and the TV signal transmission. It has led to the impact in the inventions in the field of integrated circuits. So BJT is basically the prime and the most important device that is being used in the integrated circuits. This has led to the development of all modern computers and the electronics. The basic focus of BJT operation is the use as switch. So we will be discussing the BJT operation as a switch as well as the amplification process of the BJTs. However, in this first part of lecture 5A, we will discuss more on the fundamentals, talking about the structure. When we defined the BJT in terms of the semiconductor device, it will be using the free electrons and the holes. We have discussed this in very detail in the very prime lectures of the diodes and the semiconductors, where how the electrons and the holes flow in the diode and then how it is being used in the semiconductor devices. When we talk about the term bipolar, the meaning refer to two polarities of the charge carriers. It is obviously the electrons, which is negative charge particles, and the holes, which are fictitious, but they are assumed to be positive charges. When we talk about the structure of an unbiased transistor, generally it will have three important doped regions, which are basically the emitter, the base, and the collector. So here we can see the structure of a transistor. The transistor is in the form of NPN. We will see that there are two types of transistors in general, which is NPN transistor and the PNP transistor. So the doping region in the transistors, where you have three important dope regions. One is the collector, the base, and the emitter. Talking about the emitter, this is basically the bottom region, which is heavily doped. So the emitter will be heavily doped. The base, which is the middle region, will be very thin and it is lightly doped. Whereas the collector, which is top region, it is intermediate doping. So the doping level of the emitter is heavy. So the current which is flowing in the emitter will also be more. So we will have two important type of transistors. One is the NPN transistor and another is PNP transistor. Talking about the doping level, since you have emitter, base, and collector, the emitter is basically the heavily doped, so it will have high electron flow. The base will be lightly doped for control over the electron flow direction. Collector, which are intermediate doping level, physically is the largest region. The emitter and the collector diodes generally will have two junctions in a BJT. First junction is the emitter base junction or the emitter diode. Second is the collector base junction or the collector diode. So if you see here the diode equivalent network, so you have basically two diodes which are connected back to back, and you have two important junction formation between the emitter base junction. So here you have one junction emitter base and another you have the collector base junction. So two important junctions are there, and the depletion layer which is formed between these different types of charges present in the emitter, collector, and the base will lead to formation of two depletion layer in the bipolar junction transistors. So it acts like two back-to-back diodes which are connected in the two junctions. What happened before and after the diffusion in a BJT? So the diffusion process is basically the free electrons in the N region, which is spread across the junction and recombined with the hole in the P region. So when you have the N region, obviously the majority carriers will be the electrons, and these should be free. In the P region, you have the majority carrier as the holes, and both will be recombining. So the result in the formation of two depletion layer that you have in the two junctions. The formation of depletion layer we have discussed in detail in the diode theory. Barrier potential, when we talk about due to the combination of these electron and hole in two important semiconductor device, one is made up of silicon, another is germanium. So when you have the silicon transistor, the barrier potential will be approximately 0.7 volt at the room temperature 25 degrees centigrade, whereas for the germanium transistor it will be approximately 0.3 volt at 25 degrees centigrade. Generally, when we talk about the semiconductor, we take the barrier potential as 0.7 volt unless and until some specific value is mentioned. So the NPN and PNP transistor, these are basically the two important types of transistor. So if we talk about the NPN type, the collector and the emitter both will be N type, and there is a sandwich of the base, which is the P type. Whereas in the PNP transistor, the collector and the emitter will be P type, and the base, again the sandwich will be N type. So with the name suggestion, you have the NPN, so P will be the base, and here you have the PNP, so N will be the base here, and other emitter and collector will be the N type or the P type. This is the circuit symbol for NPN transistor and the PNP transistor. So how to remember this NPN transistor? Generally the arrowhead, if you see here in the emitter for NPN transistor, will be outward, whereas the PNP transistor, the arrowhead in the emitter will be towards the base. So the current flow, generally the emitter current is flowing here outward, so the base current and the collector current will be inward, whereas here the emitter current is inward towards the base for the PNP transistor, so the base current and the collector current will be outward, because we will be seeing in a while that the KCL equation we write, the emitter current is equal to the base current plus the collector current. So the key points that we have discussed and which need to be remembered is the basic BJT structure and its operation. What is the importance of the doping label? So when we talk about the doping, we have discussed in detail, it is the addition of the impurities, generally the pentavalent and the trivalent impurity atoms, and what is the emitter and the collector junction in the BJT, how the depletion layers are formed, and what is the concept of barrier potential. Now let us take this discussion forward and discuss the bias transistor. So when we talk about the biasing, it means basically we are adding this voltage source. So the unbiased transistor, where you do not have any voltage source connected, it is basically acting as two back-to-back diode with a barrier potential of 0.7 volt. So these unbiased transistor is important because we need to test the transistor with the help of the digital multimeter. When we do biasing, we are basically adding some external voltage source so that the current will flow through the various transistor regions. So that is known as bias transistor. So bias transistor generally mean that we are connecting external voltage source in the transistor. So here if you see, we have taken an example of NPN transistor where we are connecting two sources in the emitter as well as in the collector region. So the basic fundamental is that if we want to operate the transistor in the active mode, the base emitter junction has to be forward biased and the collector base junction has to be reverse biased. Now what is the meaning of forward biased and what is the meaning of reverse biased, we have discussed in detail when we have discussed the biasing process in the diodes. So here if you see, this is an NPN transistor. So basically the base you have that is the hole is the majority carriers, and it should be positive, because we want forward biasing for the base emitter region. So forward biasing means that since the base is having the hole which is p type, so you will be having the positive of the source which is connected to the p type. Whereas in the collector region, what do you have is basically the collector is n type material, so obviously it is negative. So since we need to make the collector base region as reverse biased, so we want to connect it with the opposite polarity. So here you have the negative, so we have connected here positive polarity, and hence we can say this is reverse biased junction, and here you have forward biased junction. So the operation zones of the transistor can be divided into 4 quadrant concept. You have the first quadrant, second quadrant, third quadrant, and the fourth quadrant. In the first quadrant, which is the operation of the transistor generally as a switch, which you have the forward active region. Here the base emitter and the collector base, these are the two junctions what you have. So base emitter will be always forward biased and the collector base junction will be reverse biased. So we will be operating here in the forward active region. Other regions we will be discussing in the while. What is the cutoff region, inverse region, and the saturation region. Now you have the bias transistor, you have connected a source. So how the emitter electrons flow? So let us try to understand it. So now we are having the concept of biasing. So we have connected the voltage source in the two junctions and in the emitter and the collector. And the transistor that we have taken an example is basically the NPN transistor. So the emitter, which is heavily doped, now it will be emitting the free electrons into the base. So the electrons which are present in the emitter, it will be having heavily doped electrons, and it will be emitted towards the base region. The base, as we know that it is lightly doped, so it will pass the electrons on to the collector. So the emitter will be acting as the bridge between the base will be acting as the bridge between the emitter and the collector. So the heavily doped region emitter, which is having the electrons, the base will be taking this electron and passing to the collector region. So the collector, which will be collecting most electron from the base, and base is the intermediate region between the emitter and the collector. The two voltages that we are basically using is the base voltage VBB, and VCCC is basically the voltage which we connect in the collector. So again, it should be forward biased for the base emitter, and the collector base should be reverse biased. So this need to be considered when we operate the BJT in the forward mode. Now the flow of base electrons, so emitter which is heavily doped, now this is passing the electron to the base, and the source that we have connected in the base VBV, if this source is basically more or greater than the barrier potential, which is 0.7 volt for silicon transistor, it will emit the electron into the base region. So first criteria that need to be covered, or it has to be obeyed, that the potential that we applied in the base should be more than 0.7 volt. Then only the electrons will be flowing from the emitter to the base. Now this electron which is flowing from the emitter to base generally can flow in two different paths. Either it can flow left, that is out of the base through the base register and move to the source, or it can flow to the right into the collector. So these are two different options that this emitter electron can observe. However, the outcome is that the most electrons generally move to the collector due to the two important reasons. First, light doping of the base, which is long electron lifetime in the base you have, and the base is very thin, so you have the short distance to the collector. This base thickness is very thin and it is lightly doped, so most of the electron from the emitter pass to the collector rather than moving left to the source through the base resistor. The collector electrons and the current flow, if we talk about now, these electron which was present in the emitter through the base, it has moved to the collector. So the source that we have connected, VCC, will attract these free electrons into the collector region. So these electrons which has moved here, now it will move to the source which will be attracting it. The electron path, electrons will be flowing through the collector resistor to the positive terminal of the supply voltage VCC. And the summary of this current flow is basically that when you connect a source BBB that is in the base, it will drive the electron from the emitter to the base, and the collector potential VCC will draw the electron through the collector and RC to complete the circuit. So this forcing of the electron from the emitter to base and then to collector voltage will attract this electron and it will complete the full circuit. Now let us try to understand the transistor current. So when we talk about the current in the transistor, so it has to be three important current. First, the emitter current given by IE, the base current IB, and the collector current IC. So current flow representation can be either the conventional flow direction or the electron flow direction. So the conventional flow, if we try to see for the transistor which is having the form, so generally we will always be having the transistor current as IE is equal to IB plus IC. This is in accordance with the Kirchhoff's current law. So the emitter current is moving. Now you see the arrowhead of the transistor here. So all the current is coming this side, IE, and hence IB and IC should move inside the base. So this is the conventional flow direction. Electron flow direction will be opposite to the conventional flow diagram, and this is taking an example of PNP transistor. So in the PNP transistor, remember the arrowhead will be outward. If you take the example of NPN transistor, the arrowhead will be inside. So it means the conventional current IE is inside and IB and IC is moving outward from the base. Whereas the electron flow direction will be opposite to what you have for the conventional flow direction. Now if we compare the transistor current, that is the emitter current, base current and collector current, the emitter current is the source of the electron, so it will be largest. The collector current is nearly as large as emitter current, because whatever the current or the electrons which is flowing from the emitter, most of the electrons are going to the collector. Only in the base, which is very thin, and here you have much smaller region, less than 1% of the collector current. So entire all emitter current is going to the collector current, with small current being in the base. Now if we write these equations of the current in accordance with Kirchhoff's current law, then we can say that the current relationship is basically emitter current is equal to collector current plus base current. And as we have discussed that the approximation we can do that neglecting the base current because it is small, the approximately the collector current is equal to the emitter current and base current is very, very less than collector current. Now this application holds true both for NPN as well as PNP transistor. So these equations do not change with the type of the transistor, it remains the same. Now the concept of current gain we will take, one is the DC alpha. So the term alpha DC is basically defined as the ratio of the collector current to the ratio of the emitter current. So if we divide the collector current with emitter current, we get a term which is alpha. This is the current gain, and the typical values of these alpha is less than 1. And if we talk about very low power device, it will be greater than 0.99, but high power device, it will be greater than 0.95. However, it will be slightly less than 1 in all cases of low power or high power BJTs. The other one term we will introduce is basically beta. So beta is basically the ratio of the collector current by base current. And here this beta is controlling the larger collector current with small IB And beta ranges, if we see for the low power as well as high power transistor, lies 100 to 300 and 20 to 100 respectively. Now, how do we use this beta to derive the current? So, the collector current relationship will be equal to beta times the base current, and the base current will be equal to collector by beta. So, beta is basically a very important current gain factor which can be used to derive the currents in the collector as well as the base. So, the first lecture in BJT fundamentals, we have discussed about the structure doping the current flow. In the coming lecture, we will discuss more in detail about the BJTs as well as how the biasing affect the operation of the transistor. Later, we will move to the amplification process. Thank you for now.